Okay, so here we are today to talk about section 14.4, which was the tangent plane approximation to the two-dimensional derivative. All right, talked about that a little bit. I'm going to start off in a one-dimensional case here and remind you how it works. In that case, what we're doing basically is just a linear Taylor polynomial approximation to this, which you should remember for 191. But we're going to show here now, after I remind you of this example, how it works in two dimensions, which again is just a linear approximation, but we have two variables, so there are two steps, but it's morally exactly the same. So let's remember exactly how this works. So anyway, 14.4, the geometry of derivatives and linear approximations, all right? 14.4 is, of course, two-dimensional functions. We're starting in one to help you remember how it goes. Okay, so anyway, the function that we're looking at here, and I guess it's here somewhere, but anyway, the function, oh, here it is. So the function that we're going to play with here will be a nice simple function that we can play with, namely the square root function, okay? Now the trick about these Taylor expansions, if you remember, which is this equation down here. You know, here we have the first few terms of a Taylor polynomial. Now here I've kept, there's the function expanded about the point x naught. There's a linear term here involving the first derivative. The next term involves a quadratic, and of course, the Taylor series goes on forever. The Taylor series has the property that it's exactly equal to the function, but one of the tricks, one of the things you do with these things is that we truncate these polynomials to get approximations to numbers. It's a little bit of an old-fashioned thing nowadays that everybody uses computers and everybody knows how, but just once again, you need to be exposed to have some idea what goes on in these numerical methods, and so this is maybe the most basic example of the way numerical approximations work. So let's just remember how it goes. All right, so anyway, here's the curve. Y is square root of x. And when you do these things, the trick is you've got to know a point where you know about the function. And then using that information, you try to find out approximations to the function value for points nearby to where you know it. So we're talking about a square root function. The candidate expansion points, again, are the places where we know what's going on with square roots. And on this picture here, we've got some of those shown. For example, 1, 0 would be another one, but we won't pay much. 0 is boring for this. We won't pay much attention there, but 0 is there because we know root 0, 0. 1 is a good point. We know that the root of 1 is 1, so the value of y is known there. At 4, we know that the value is root 4 is 2. At 9, the square root is 3. So those basically, if square root function is what we're playing with, then these are more or less our candidate expansion points. Places where we know about the function and its derivatives, so that when we go to evaluate a Taylor polynomial such as this one, we can do it, okay? So anyway, I've drawn the picture here focusing on the point 4. So we're taking here basically our point of expansion, which we'll call x naught, and that will be 4. Doesn't really matter which of these you use, but that's a nice one right in the middle of the picture so we can see it. So, you know, here's the point. 4, square root of 4 is 2. So the tangent line goes through that point, and of course is tangent to it, duh. And then, okay, and so basically that's it. So here, that's one interpretation then of a one-dimensional derivative is as, well, of course, the derivative itself is the slope of the tangent, but the tangent line itself, then the linear approximation, is again a useful representation of the function. So let's use our knowledge that x equals 4 to find an approximation to a square root point that is of a number that's close to 4. That's the trick. You have to look for values close to where you want to find it out. You know, 6 is pretty close to 4. It's pretty close to 9 too. We could have done this at 9 as well, but we'll go ahead and do it at 4. Right? So anyway, the tangent line then, as we see up here, is of course a linear function. And so you can kind of see, you know, this curve are the exact values of square root. So, you know, the exact value of square root is the number on the dark curve. But then above it, the number on the tangent line curve, which I think you can just about see, which you can see is actually a little bit bigger than the actual square root of 6. Should be able to see that's not a bad, it's going to be a pretty good approximation because the curve and the tangent line remain close together at that point, right? Anyway, so we have to compute these, you know, the function of the point, the derivative of the point, and then the linear term. If we wanted to keep going and get better approximations, we could include the quadratic term, but that's not what we're doing right now. So anyway, let's go ahead and compute this. So once again, our function is the square root of x. Our expansion point is 4, so the value of the function there is 2. The derivative of this function is 1 over 2 root x, again, things you have to be able to know how to do. And the derivative at that point, the slope, the derivative, then the slope of the tangent there, the derivative, is then 1/4. Okay, so anyway, if, let's see, if we keep only the linear terms, here's the approximation we want to solve for. So once again, so there's the equation. So basically what looks like this is, let me finish this off. And so what this looks like then is f of x naught is 2 plus 1/4 for the derivative, and then x minus x naught or x minus 4. Okay. And that then will be our approximation to the square root of 6. So let's come up here. That's where we did all these things. And so this says then that root 6 is approximately then 2 plus 1/4 of x minus 4. If x is 6, that's 2 plus 1/2. That gives us 5/2. So a fractional approximation here to square root of 6 is indeed 5/2. And if you look just by way of comparison, ask your calculator, and you will find that the square root of 6 is actually 2.449. And all I'll point out is that that's really a pretty good approximation for just a linear term, that's 2 units away, not even that close. So this really does show how the linear approximations do give useful numbers for these things. All right? So anyway, that's the reminder. And let's now just move on then and start talking about 2 dimensions. So anyway, there's a couple comments before we get going. So one is to say that 2-dimensional approximations pretty much work in the same way. But of course, there are now 2 variables that we're going to have to deal with, right? Anyway, though, we have to be able to write the equation for the tangent plane just as we wrote the equation for the tangent line in the previous example. Well, we learned how to do that way back in chapter 12. And so just let me remind you of that, because we'll need this, to proceed from there. But if you remember, it looked like this. So it was a linear equation once again in the 3 variables x, y, z. And we saw that, and so there we are. That is the most general form of a linear equation in 3 variables, x, y, z. Remember that in this expression, n was a 3-dimensional vector whose components are these ABC coefficients. And remember that the way we work this out, that vector is the perpendicular vector to the plane, right? That's the normal vector. This number D on the left-hand side, if you recall, was a number, a scalar, that came from the geometry of the plane, where again is the normal vector. And remember that in order to specify this, you had to know at least one point that could be in the plane, because when you think about just the normal parts, I mean, I could have 2 planes that have the same basic normal vectors if I hold them up like this, parallel to each other, right, or maybe something like that. However, these are not the same plane. Why not? Because they don't contain the same points, right? Even though the normal vector is the same, this contains this point, that one contains a point down there, so they're not the same plane. And so that's what that reflects. That's the difference. So any vector with the same normal vector has this part of its equation, but this one determines which point, determines which plane it is due to which point is actually in there. All right? So anyway, you can rewrite that as something like this. AX plus BY plus CZ equals then A, say, X naught plus BY naught plus CY naught, where again, A, B, C are the components of the normal vector. X naught, Y naught, Z naught here, sorry about that, are points known to lie in the plane, known to lie, in the plane right there. And then here, has the variables X, Y, Z, and so remember what this means is, we know the numbers A, B, C, X naught, Y naught, Z naught, then every 3 points X, Y, Z we can find that satisfy that equation are points that live in the plane we're talking about. So this is how we specify these things. Right? So anyway, just kind of like we did before then, if I want to find out an approximation to Z, it would be something like this. So what we want to do here is, again, so find an approximation to Z at a point whose horizontal components, x, y, are some, again, known points that we're after. That's what we choose those generally. That's what we chose to be for in our one-dimensional example, right? So we find the approximation there at that point. Where the exact value that we're looking for Z is the two-dimensional function at X and Y. Okay? So once again, we're going to take this guy. We're going to approximate the original nonlinear function with the plane and solve it to give us these approximations. Okay? Anyway, so in other words, we know a point Z naught that happens to be the value of the function at a point X naught, Y naught, close to the point where we're looking for our stuff. All right, anyway, so you put all this together, and I'm gonna not get into too much detail here just because I don't want to make too much of a mess. But anyway, it comes out this way then, that the approximation for the number Z that we would be looking for is then about equal to the value of Z at the reference point near to where we're looking for. And so what I'm basically doing is taking this equation, solving it for Z, and so what you end up with then is this. Let me get it written up here. You should be able to see it. That looks like that. So that basically compares to what we were just looking at. Remember where we said that, our function y and the one-dimensional function which again looks something like that. Remember, that was a straight line. So you can see what's going on over here now. It's really just the same. Don't worry too much about the A's and the C's and the minus signs. Those are in there. We'll change those up a little bit to be more familiar now. But the point is here, we just now have, like, instead of one term here, we've got two terms, one in each variable. Other than that, knowing what this function is, the whole Taylor approximation works exactly the same. Okay? So anyway, we need to find the equation of that plane so that we can solve for such an approximation. So let me, with great trepidation, try to do a little picture here of 3 dimensions that we can get a picture of. Right? So in 3 dimensions, with the usual right-handed coordinate and that kind of a layout, say that there's now a surface here. Let me try to kind of draw it like that. Okay. And the idea that's just supposed to be a piece of a curved surface sitting there, right? Anyway, so up here we have a point on the surface. You know, we drop it down to the projection of the XY plane. You know, so there's the Y naught value. And there's the X naught value. So basically this will be the point about which we are expanding to get our approximation. Okay, and so again, you know, this guy comes over here, he's got a value of the Z coordinate, and this picture implies, you know, and so this is my curve that I'm trying to draw here is the graph of the function Z equals f of xy, and the picture implies that x naught, y naught, z naught is a point where we know about things, and so we're going to use that information to approximate values nearby. All right, so anyway, now the point, so we got to find the plane. We need a normal vector. Well, we know how to find normal vectors. We know how to find these planes. Basically, what we have to do is find 2 vectors that would be in the tangent plane at that point. And then we need a perpendicular vector to that. So what do? Of course, we take the cross product. And that will give us our n. Okay? So let's look at that a little bit. All right, so let's focus in here, just to, again, trying to keep my picture as legible as possible, which, as you know, is a pretty darn tall order for me. But let's say that this is a curve in the surface, and let me refer to it as L. I think that's a letter that's in the book. It doesn't matter what letter we're using. Okay? So anyway, let's focus on that. Now, the thing is, now there's a plane tangent to this. I think that's something, you know, the way it kind of, well, I'm not going to get into that. You can look at the book. The book talks about that. I talked about it the other day in our Zoom meeting a little bit, so I won't get into it there. But anyway, in this plane, there will be, say, a tangent vector in that plane, which will happen to be parallel to the y-axis, say above this curve that's up there. okay? So it's going to be, say, for a fixed value of y, and we can compute, actually, just by thinking a little bit about one-dimensional Taylor expansions, what the form of that vector u is. Similarly, then, by the same logic, I can write down another vector, which would be, say, perpendicular to this one. Say another curve that goes in the other direction again. I think P again is the letter you find up there. And so there's going to be another vector in that direction. So what I do to find the form of the vector u will work exactly the same as finding the vector v. We can take the cross product, we get the normal vector. We know a point in the plane, don't we? So everything I needed based on the stuff I had on the previous exam, I can figure out, and I can then use to do an approximation of the type we saw before. Okay? So anyway, just to keep the picture simple, let's focus on L and see how to get an expression for U. And then I'm just going to write down the expression for V. And once again, go look at your book, because the book goes through this discussion just as well as I do, so you can compare, right? So anyway, let's go ahead and think about taking a vertical trace. Remember that word? Let's think about the vertical cross sections of this curve that contains this curve L, and see what it looks like. Okay? So anyway, we'll have a set of axes. This is basically the L axis. I'm being a little sloppy writing it that way, but I think you get my idea. And so this L curve will look something like that, right? So once again, that's L. All right? So anyway then, say at this point x naught, the place where we're looking there, then, that corresponds to that point on L, and the vector u at this point is going to be a tangent vector to L, just sort of as I've indicated there. What's more, you can see that, you're going to get you can write it as a right triangle like that. And remember, this is all along here, so let's see, I guess x naught is fixed, is the way we think about this, right? Because we know right where it is. Let's see, hang on just a minute. Let me think about that for just a second. Yeah, x naught is fixed, and so basically what I probably should have written over here is the vector y, because the way it's supposed to be drawn is that the curve L is over this curve down here at the fixed x naught. So in this picture, x naught is fixed, and y varies across all those numbers there. So this is basically the projection of the y-axis. It's actually out here, but still the y-coordinate tells you where you are. Right? So anyway, the slope of this derivative up here, let me write it here, down here, say, okay. So the slope of the hypotenuse of that vector, or of that vector, you could then work out and you can find out that, we're holding x not fixed. So this is actually, this would be the partial derivative with respect to y evaluated at the points x naught, y naught. Like that, okay? Now, when we're writing down vectors, I don't really care here how long u is. Doesn't have to be a unit vector here. It doesn't really help us all that much. And since I know that's the slope, well, I can normalize the vector any way pretty much I want, so I'm free to think of the length of the bottom of that vector as being 1. Okay? So anyway, when we put all that together, then u, the u vector that we have here, comes out to be, okay, well, it has no x component, right? Because it's parallel to the yz plane. The y component has length 1, because as I was just saying, I can choose it to be 1, and it's convenient, so let's just do that. And then therefore, the z component, because that's the slope, turns out to be fy of x naught 1. Okay? So there's one of our vectors. Nothing in the x component because we're in that plane. Normalize my vector so that that's a 1. And then the slope tells me that the y value must be that. If I did the same thing in the other direction, we find out that the vector v, sort of by the same token, is like that. So now for this one here, our y values are held constant. Say that, it would be a line along here. Once again, so, that's that. I can choose my x length to be 1 for the same reason. And then that's our z value. So I found u and v, as I promised I would. And I can now, right. And I can now compute the normal vector. Okay. So let me do that. We're almost done. This has been a long lecture, I know. I didn't really intend for it to go on this long, but we're almost finished. So hang on for just a little bit longer. So anyway, our normal vector is n. Alright, which is one of our usual cross products that I will use oops, hang on here, my bad. Did I do that right? 0 and F4, my bad. Sorry. Write that down there, that's good. And then 1, 0, Fx. Right, so in our usual determinant notation, the normal vector comes out that way. And when you do the computation in the usual way, you get these results. And remember, these are all evaluated at x naught, y naught. Tell you what, I'm just going to leave those off for simplicity. All right, so anyway, y gives us that, right? If x gives us 0 minus that, but the minus sign gives us a plus, and the z vector gives us 0 minus 1. So our normal vector actually comes out looking like that. Okay, so anyway then, putting all this together, our approximation formula that we had last time comes out to be this. Okay, that z is approximately equal to z naught, which, you know, is the value of the function at our reference points, whichever we've chosen those to be. And then we have two terms that give us the so-called linear corrections to the number that we're looking for. Okay? So anyway, let me get this up here. And there we go. So go back and look at the other stuff we just did. And that was the stuff, the same kind of thing. All right, so anyway, that's basically it. There's the formula. So just to finish things up, let's go ahead and do an example and show how this works. And I'm just going to do another square root example because those are very simple and you saw how it worked in one dimension. So let's see how it works in two. So anyway, having that, here's the formula we're after. And so let's look at a particular function. And this one again is nothing particularly special about it. It's complicated enough to give us a little bit of work to do and see how it works, but not much. Let's just take that function. And let's say we want to find an approximation to, kind of a funny looking number here, but let's say it was this. So this is kind of a joke, you know, so it's like, let's say we're trapped on a desert island somewhere. We're on Survivor. How's that on CBS? And so they're offering us $1 million to give somebody $1 million if they can find a good a good rational approximation, a fractional approximation to that number without using a calculator. All right? Only the mathematicians would have a chance to win this one. So we're just going to use these formulas. You know, there's our f. We've got to find some derivatives. Now to proceed, we have to choose our expansion points, these x naught, y naughts. And we have to choose them in such a way that we know about our function at those points and its derivatives so that we can work with this stuff. Well, that's really pretty obvious. I won't beat around the bush. But to do this, let me just write this up there. I need 2 points, x naught and y naught. I've chosen x to be the one at the top and y at the bottom. Nothing deep about that. We could have gone the other way. You just got to pick one and stick with it. But anyway, so x naught, I need a point near 8.9 where I know about square roots. That's a pretty obvious answer, isn't it? So I won't beat around the bush. I'll just point out that the number 9 is very close to 8.9, and I know that the square root of 9 is 3. So I can evaluate these things by hand quite easily. Similarly, of course, then, y naught is 3.8. And so the obvious, and so the obvious point to take to do the expansion is 4. Okay, let me write this here again so that we can use it down below. So, for example, the value of the function at these points, is going to be the square root of 9 over 4, right? And of course, that's just the nice round fractional number of 3/2. All right, so that's what I mean. We'll have nice numbers to work with, and you'll see where we end up at the end. All right, so anyway, like I said, I'm just rewriting this up here so we have it at our disposal. So, let me just write it the same way for the time being, and then we'll do the calculations. So it's just that. We need the partials. Again, at the expansion points times the linear increments. All right, so this is the formula that we want to end up using. All right, so anyway, let's get rid of this. Let's just do the calculations, stick them up here, realize too, okay, these are the x and y, right? So these are x naught, y naught. So the x that we're after, the place we want to know, corresponds to 8.9. And the y value itself, where we want to know what's going on, is 3.8. Okay, so anyway, there we go. So like I said, we did it up over there. We got the 3/2. We need a couple derivatives to proceed. So the partial derivative of this function, the square root of x over y, tell you what, I'm not going to go through the steps here. I'm just going to write it down. You guys make sure you know how I did this. And this answer comes out to be 1 over 2 times the square root of x times y. Right? And so in particular, too, then, in this expression, we need that derivative at x naught, y naught, at 9,4. And easy enough, I think, for you to verify that that number comes out to be 1/12. All right. On the other hand, Fy, then, by the same token, comes out to be minus 1/2 times the square root of x all divided by y cubed. Okay? And so once again, in order to use this in the formula, we need to know what that derivative was at that point. And once again, we know those, so we can do these in our heads, practically, certainly on scrap paper, if nothing else. And you should be able to verify that that gives us 3/16. All right, well, now we know everything. So I can find the approximation, which is that number. If I know this number, which is 3/2, this number, which is 12, x, remember, is 8.9, x naught is 9, Fy is minus 3/16. y is 3.8 and y naught is 4. Right? So anyway, here we go. And so the approximation we get says that the square root that we're looking for of 8.9 over 3.8 is approximately equal to the function itself, the value of the function at that point. Going to this is 3/2, right? And then we have this term, so plus 1 over 12 for that slope, and then this term here gives us x minus x naught. Let me write it out so you can see the details. That would be x minus x naught. So there's that first term. Then we have this one. Now the slope there is negative 3/16. The signs are important. You have to be very careful to get the signs right. Okay, and so we got that one there. And then once again, that multiplication is 3.8, or subtraction rather, is 3.8 minus 4. So once again, let me just call your attention here, that here is the linear polynomial with the two variable linear expression that gives us the approximation. So over here on the right hand side, we have 3/2. Now 8.9 minus 9 gives us a negative 1/10. So all in all, this term, this next term here, is going to give us a negative minus 1 over 120. And then this one here again, 3.8 minus 4, gives us a negative 2/10. Again, a minus sign there. So put all this together, and the next term that sits here turns out to be 6 over 160. Okay, so like I said there, here's an approximation to this weird number as a sum of fractions, because it's a rational approximation because they're rational numbers. And of course, you can bring these guys to a common denominator, and should. And so it comes out to be, well, on the surface right away, 734 divided by 480. And you can reduce that fraction, and you get 367 over 240. Right? And again, that gives us a so-called rational or fractional approximation to that number, which was obtained as a two-dimensional first-order Taylor polynomial in two variables. Works the same way though, and again, this is not the way it's really done in real life, but it's an interesting moral lesson, the way you take an answer that's close and produce a new one. These algorithms illustrate the sort of things that go on in these numerics. Okay, so that finishes 4.4. So we're about halfway through chapter 14. We'll keep working on this, and I'll try to get a couple more up from the later sections between now and our next meeting on Tuesday, and then we'll discuss where we're going from here. So that took way longer than I thought. I did not expect that to go a whole 50 minutes, but I don't know. I guess I'm still learning how to do this. So end of that. We'll talk to you guys later.